speaker, Shude Mao, and he's going to talk about galactic dynamics, MaNGA view.
Okay, so I'm delighted to be back at CFA. I noticed I came earlier than most of the speakers, actually all the speakers so far. So when I arrived, I think we only had theory division. It's not yet called ITC. So this is my early pictures. You can see I was young and full of hope. I know which class I belong to in Abe's classification. And at that time, I also had access to very powerful computers, more powerful than Volker's computer, and wonderful monitor, as you can see. I collaborated with Abe, Rosanne Di Stefano, and Ramesh Narayan, who is in the audience, Chris Kochanek, since I guess he has left, Sivi Piran, and Paul Schechter, who were visitors at that time. So let me tell you maybe two little stories I had when I was here. So one day, Abe came into my office, obviously hugely worried. He told me that he had he may be writing reference letters, and he said, I have this wonderful student. He is my best student, but the problem is that he is my only student. And he was talking about Daniel Eisenstein. So looking back, his worry was not so justified. I'm just wondering whether he will say the same thing today. His first student is still his best student. And then I moved office at CFA once. And once I moved into my new office, I often heard noise from my opposite office. And I was a bit annoyed. The only word I can hear very clearly was supernova. And it turns out it was Adam Rees discussing supernova with Bill Press. So I don't remember. I was extremely impressed by their discussion. But obviously, my criteria was not so good, okay? So when I was at CFA, I mostly worked with Abe on lensing by clusters of galaxies, and with Rosanne on microlensing, with Ramesh on gamma ray bursts. But I have, since I left CFA, I worked on a few other things like galaxy formation and galactic dynamics. And this is what I'm going to report to you about the work we have been doing on IFU survey data with MaNGA. So this work is really due to two postdocs, Kai Zhu and Shengdong Lu, who is now a postdoc at Durham, and Kai is a postdoc at Tsinghua University, and two senior astronomers, Michele Caprari, putting a lot of effort into this work, and Ran Li from NOC. So this is a series of papers, about half a dozen papers on the dynamical studies of 10,000 MaNGA galaxies. So let me start with motivations and a brief introduction of MaNGA, and then go into how we do the dynamic modeling and the stellar population synthesis, and discuss a little bit of scaling relations and what we might be missing in simulations, and finish with a summary and future outlook. So, well, this really is my main motivation. You can see on the left the beautiful images from JWST, the fan survey, and with the exquisite details of galactic structures. And on the right, you have TNG50 simulations of spiral galaxies. You can clearly see these simulations, which can be done by many in the audience, Volker, Lars, and Mark, and many others, which I subsequently collaborated with. You can see that the morphologies are reproduced very well, but one can still ask questions whether the dynamics, instead of just the photometry, are reproduced by these simulations, especially the central dynamics, because you have limited numerical resolution, and how dark matter and stars are mixed, and obviously want to use the dynamics to put constraints on how galaxies form and evolve. So the MaNGA survey is the largest local IFU survey. It has about 10,000 galaxies. Redshift range is given here, 0.01 to out to 0.15. So this is really a local galaxy sample, and it's mostly mass selected, mass from 1 billion solar masses all the way to 10 to 12 solar masses. So some of these are quite massive. And the data has already been released in 2022, but we are still working on the implications of the data set. So as you can see, with IPU of fiber bundles, you can resolve a lot of information, including H-alpha emission, which you can use to understand star formation, and also D4000 break. You can use this to understand stellar age. And of course, you have dynamics from gas stars. Here shows the average velocity. You can see clear signs of rotation. And of course, you can go beyond the average velocity, look into the second order moments like velocity dispersion. So really, it's a huge challenge to understand the connection between chemistry, metallicity, and dynamics. So this is really a valuable database to look into the chemodynamical evolution of galaxies. So how do we do dynamic modeling? We have a number of ways, like made-to-measure method, structural method. So because those methods are quite slow, so we mainly use the genes and isotropic modeling, so-called GEM. So it goes like this. So you have a 2D photometry. So assuming some inclination, you can kind of deproject into a three-dimensional luminosity density distribution. So assuming a constant mass-rate ratio, you can then infer the total density and thus the potential due to stars. And then from previous speaker, we are convinced that the dark matter halos may be NFW. So you assume an NW profile, then you can assume, get the dark matter potential. So by adding these together, you get the total potential. So now assuming some sort of velocity ellipsoid anisotropy, you can use Jeans equations to obtain the second order moments. This is the square root of the rotation velocity squared plus velocity dispersion squared. So this is the predicted, what we call VIMS. And you can compare with this with the observed map to infer the model parameters like stellar mass-rate ratio, inclination, the anisotropy parameter beta, and some parameters in the NFW profile. So from this, you can infer the mass profiles, stellar contributions, dark matter, and the total contributions. So one significant advantage of this series of papers is that we use two velocity ellipsoids, cylindrically aligned, spherically aligned, and four dark matter profiles. One is NFW, generalized NFW, mass follows light. So this is not saying you don't have dark matter, it just says that dark matter follows light. So we have two velocity ellipsoids and four dark matter profiles. So in total, we have 8 models to explore not only the statistical uncertainty, but also systematics between different models. It turns out different models give more or less the same results when the data qualities are good. So let me show you, 24 example galaxies of data. This is VRMS data, and this is the model data. So you can clearly see some are modeled better and some are not so well. In fact, we have classified 10,000 galaxies into 5 classes. For example, quality 3 is the best. So you can see that this is the data, this is the model. The second order moments, VRMS, you can see they're reproduced well. So is the mean velocity, first order moments. So this is quality 3. And quality 1, you can see that VRMS shape are reproduced. So that you have a central peak and then a decline, but the values are not very well produced. So from quality 1 to 2 to 3, you have about 6,000 galaxies, which we think can be used for dynamical analysis. So for quality -1, you can see that this often shows irregular photometry and kinematics. These may not be in dynamical equilibrium, so they are not very much used in our subsequent analysis. So we also did the stellar population synthesis. One faculty here, Charlie Conroy, is a world expert on this. So you have single stellar population with some age metallicity. Then you have different weights, and you use these single stellar populations and these ways to predict the spectrum and compare with observations. And then you can infer the age, metallicity, stellar to mass-rate ratio, and star formation history, and others. So we did this also for 10,000 MaNGA galaxies on top of the dynamic analysis. So let me show you the stellar population results first. So this shows the log effective radius versus dynamical mass obtained from JAM. So you can, this shows as a map of age, metallicity, and stellar to mass ratio. So these are smooth maps of 10,000 galaxies, so-called low-S smooth versions. From these plots, you can clearly see that the size and mass follow systematic trends in these. So these dashed lines show different lines with different velocity dispersions. These 50, 100, 200, 300, 400, all the way to 500 kilometers per second. So you can see the colors from young to old clearly show more or less along the velocity dispersion line. Similarly for age and metallicity. So larger galaxies are older, more metal-rich, and also have a larger stellar to mass ratio. This is consistent with previous studies. Now, we also look into the rotation parameter lambda RE versus ellipticity of these galaxies. So this lambda RE is defined here. So basically, the larger this parameter, the more dominant the rotation is. So you can clearly see in this plot, for example, ellipticity versus lambda RE, colored by age. So red means old. So these are so-called slow rotating region. So they are very old, and you move up in the lambda parameter, spin becomes more important, and the stellar population becomes younger. So these galaxies are younger galaxies. And similarly for metallicity and mass ratio, they have systematic trends, and these trends are the largest data set that have been used for this purpose. And these still need to be understood from simulations. Now, you also see this population, and have large ellipticity and sometimes reasonable rotation parameter. And these turn out to be edge-on galaxies, seem to be youngest and most metal poor because you are seeing edge-on. You don't see much of the, due to dust, don't see the old bulge. So they appear to be young and also have lowest stellar mass ratio. So these systematic trends still need to be compared more fully with numeric simulations. Now, we also look into the stellar population gradients. So you can also in the plane of size versus dynamical mass, also you can see very clear trends in this diagram. So to understand this, we use this plot by Michele Caprari, size versus stellar mass. So he divides galaxies into different classes, lower mass into dwarf irregular spheroids, late spirals, and then the most massive slow rotators and fast rotators here. So if you look at the color gradients, they clearly show systematic trends. For example, galaxies with the most negative gradients, in this case, somewhere here, and they are really these bulge-dominant galaxies where the bulge, they have very old age, and you have young star-forming disk in the out part. Then in this case, the gradients are negative, as you can see from here, and also in age, metallicity, and stellar to mass ratio, all consistent with this trend. And then you have galaxies, low mass galaxies somewhere here, so they have nearly flat population gradients, as indicated by these colors. So they are all clustered around 0. And these are really disk-forming galaxies. So they are forming stars all the way through the disk. Therefore, the gradients are nearly constant, nearly flat. So these are the low-mass disk galaxies. And then the most massive galaxies, again, have flat profiles because, as you can see, in these places, their colors are also consistent with more or less 0 gradients. And these are slow rotating galaxies where the star formation has been quenched. So you have no star formation, then the stellar properties are more or less the same across the galaxy. So from this stellar population gradients, you can clearly uncover some information about how star formation is proceeding in different types of galaxies. Now, in fact, our scenario is consistent with the scenario proposed by Van Dokkum, how galaxy may evolve in the size versus stellar mass. So he divides the galaxy growth into two modes. One is gas accretion-induced star formation. The other mode is giant mergers. So from our plots, this can be clearly seen. So for example, in the gas accretion-induced mode, you have, so this is the effective radius versus the dynamical mass. So in the gas accretion-induced star formation phase, so this is the total density slope. So I think the blue one means shallow density slope. As star formation proceeds, more stars collected at the center of galaxies, so the slope becomes steeper, as you can see from the color. And also, the fraction of dark matter in the central part within the effective radius increases. So this is because more stars collected at the center, so the dark matter fraction actually decreases along this line. Similarly, you can see that in this track, actually the spin parameter lambda does not change very much. Now, in the giant merger case, you can see what happens is that these galaxies have a slope similar to the isothermal. Doesn't change as very much as this giant merger proceeds. And also, dark matter fraction doesn't change very much. But in the lambda plot, the evolution is quite substantial. You can see the spin parameter decreases because you have more random motions due to minor mergers. So this lambda parameter actually decreases. So this scenario actually is very consistent with what we have in the data. Now, I want to say a few words about the initial mass function. So this alpha parameter is the stellar mass-to-Dwyer ratio. We infer dynamically. This is tracer population in dynamic modeling, so we can infer this quantity and compare with the stellar population value. Now, if the dynamic mass and stellar population agree with each other, then it means you'll assume initial mass function, which in our case is salpeter. So this plots log this parameter. So it's 0, it means 1. So you can clearly see at the more massive end, indeed, these galaxies have initial mass functions consistent with salpeter, in some cases even steeper. Now, if you go to lower mass galaxies, in fact, this parameter becomes smaller. It means the mass is smaller, dynamical mass. So what it means is, in fact, the initial mass function is not salpeter. In fact, it's more close to a Kruper initial mass function, where this the stellar population mass will be lower. Now, so you can clearly see a mass trend of this of the initial mass function, and this is not yet fully taken into account in numerical simulations. Now, we also look into whether we can see the differences in the initial mass function with lines using the sodium-1 absorption line. So we divide the sample into different categories, for example, the same dispersion, but low alpha value and high alpha value. And the high alpha value is the black line. If it shows some difference, then the absorption in the black line should be larger, but we don't see this any trend. Similar with other classifications. So from the stacking of spectra, we don't see significance in the lines. It means the data quality still need to be better. So this is what I'm going to say about stellar populations. So I want to go to scaling relations. So this is the usual fundamental plane for early type galaxies and late type galaxies. This is luminosity as a function of sigma E, dispersion, and the size. So you can clearly see that for early type galaxies, this fundamental plane, if it's plane, then it's a single line, but it does have scatters. And the scatter you can see, vertical to the fundamental plane, this line, you can see systematic differences perpendicular to this line with age, and also for late type galaxy, at least at the massive end, with age as well. So the dark matter fraction for early type galaxy remain to be low, a point that I will come to next. So this is for fundamental plane, the luminosity as a function of sigma E and RE. We also look into the mass plane. So this is the dynamical mass. So from Beer theorem, you expect this parameter B to be 2, and this parameter C equals 1. So mass scales as sigma squared times R. So indeed, this is what we find. The slope B here is close to 2, and C is close to 1. So this is the same for early type galaxies and late type galaxies. So I want to point out that this scatter in the plot is not due to the homology, difference in homology in density in the luminosity profiles, because as you can see, for different statistical indices, the colors don't change vertically to the line, instead along the line. So the scatter is not due to different statistical profiles. So one thing is quite clear. For both early type galaxy and late type galaxy, they observe the Beer theorem quite well. Now, the next thing I want to come to is for the dark matter fraction. So we did this for 6,000 galaxies with quality better than 1, 2, 3. You can see different symbols when the dark matter is modeled as an FW profile or generalized FW profile. So you can see for quality 3 catalog galaxies, some of these galaxies have large dark matter fraction because luminosity usually steeper than the NFW profile. When you adopt the generalized NFW, then you can somehow you adopt a steeper profile, so the dark matter fraction at the center would be higher. So this is a smooth version of the same thing. Now colored by age, so you can see the more massive galaxies are older, and low mass galaxies are younger. And you can see two different lines here. For example, for NFW profile, the dashed line is for quality better than 1 galaxies, and these triangles are median values for quality 3 galaxies. So what you can see is for massive galaxies, from our dynamic analysis, the fraction of dark matter is quite low, and then it increases when you go to lower mass, all the way to about 50% for the lowest mass galaxies. So this trend is clearly seen in both models. Now, if we compare this with simulations, and this, for example, I think one of these simulations is due to Eagle. And this is for the early type galaxies in our catalog around 10%. So clearly numerical simulations appear to predict a lot more dark matter within the effective radius than what we see in real galaxies. Now, we also compared the total density slopes as a function of virial mass and as a function of sigma E. So the MaNGA curve is somewhere here. So you can see increases from low mass galaxies to high mass galaxies. And it's not really completely isothermal. For more massive galaxies, the slope is actually steeper than the isothermal slope. And you can see TNG 50 and TNG 100 predictions. And for more massive galaxies, TNG 100 doesn't do very well. Now, this is also seen in the dispersion plot. So at this end, I think TNG 50 at the massive end does quite well. But at the low mass end, both simulations tend to produce slopes steeper than what we see in MaNGA. So not everything is consistent with each other between observations and theory. And as Borg was saying, this may be exciting because it keeps theorists and observers both employed. So I think on that optimistic note, let me finish with a summary and future outlook. So I want to emphasize this is really the beginning of systematic studies. So we provided a 10,000 galaxy MaNGA local dynamical sample, well-calibrated, quality assessed, and this needs to be further explored. And we studied the stellar population properties, initial mass function, which needs to be, I think, in the future, somehow incorporated in cosmology simulations, and studied scaling relations and found some differences between observations and theoretical predictions. And we are currently trying to combine these dynamical studies at the central parts with weak lensing data in the out part, and also with H1 observations. And clearly, in the future, I think we need more comparisons between local and high redshift, between simulations and observations. Particularly, we appear to see, for example, bar galaxies at redshift out to redshift 2 or 3. Are those bar galaxies similar in dynamic properties as their local counterparts? Or are they just like these galaxies? In fact, they have quite different properties. And our ultimate purpose is, of course, to put stronger constraints on how galaxies form and evolve. Thank you.
Questions for Shude? Yeah.
Well, just to start off with, so the MaNGA is a style of, Japanese style of art.
Right.
What does it mean to you? How did you come up with that name?
I think actually I learned that Jim Gunn at Princeton made that name. I think he likes Japanese culture and Japanese cartoons. So I guess this is rather modest, maybe in his style, that we want to put a preliminary MaNGA-like view for dynamics of galaxies using a local sample of 10,000 galaxies. And maybe this will be superseded by the Hector survey in the future with 15,000 galaxies, but they may be a few years down the line. Mm-hmm.
More questions?
So I think from a theory point of view, these low dark matter fractures are really concerning for us because we this is not very easy to put the galaxies in different dark matter halo places because we cannot really get the dark matter out of the halos at these scales. So the question I'm having into your analysis is it really so tightly constrained that aren't there degeneracies, especially with the mass to light ratio, so that you can somehow get mass models that have more dark matter, or what's the view on this?
Right.
The error bars are very small, right?
These are the median values, so the error bars are small. But as you're absolutely right, for individual galaxies, they have huge scatters. But I trust the median trends more. Even for the same mass, the scatter is huge, as you can see here. But I think if you produce 10,000 galaxies in TNG, then this sort of median trend, I think you need to pay more attention to. Individual galaxies, as you know very well, the stars and dark matter have degeneracy. Yeah. Mm-hmm.
Maybe it's along similar lines on the kind of modeling aspects. It's one thing that we've learned in the Milky Way with results from 60 kinematics is that it's very much in this equilibrium, even though it appears kind of that it has a thinness and like everything is regular. So just wondering kind of what's your take on the role of, or the assumption of this genes analysis and here, and whether that could be causing some of these very low inverted effect fractions.
Yeah, you're right. So some of these are clearly in dynamical disequilibrium, right? But for these 1,000 galaxies, you can see that both the second order moments and the first order moments are reproduced well. So I have high confidence. And in the dark matter fraction plot I have shown, there is one median line for these highest quality data. So I would certainly trust these galaxies much more. These are fast rotators that are reasonably well understood. So I would be a little bit concerned, but for these highest quality data, I wouldn't be that concerned. I should also maybe mention that in that same plot, you have results from structural models. I think in this diagram, for example, in this region, these results are more or less consistent. For these galaxies, somehow they are higher than what we have found. So at least in this region, appear to be a general consistency between structural models and jam models. Yeah.
Any more questions? Okay, if not, let's thank Shude again.